Let's continue talking about stereoisomeric relationships. So I'm going to give you pairs of molecules. Now we're doing problems. And we're going to decide what are they related to as enantiomers, as stereomers. Are they the same molecule or something else? So for that, I need to be drawing from my handout here. So let's say need to have here an OH, and then here that's dash, then have an OH, and then the other molecule that I have to compare it with has an OH here, and here has that. So the first thing that we need to note is how many chiral centers we have in the molecule. So I'm going to put a square to those. So this is one chiral center. We have 4 different substituents, this chain, OH, and H. Here you also have another chiral center, right? And here you have another chiral center. So we have 3, same thing here. We notice that where the OH is, the configuration is inverted. Then where the chain is also inverted. Notice here's dash, here's wedge, but it's not inverted here at the other chiral center. So inverted, this 2, and the other is not. So they are related as diastereomers. Remember that if they were enantiomers, every chiral center must be inverted at the opposite configuration. And here we can do the absolute configuration of the carbons and see, for example, that one here with the OH is highest priority, then this chain to the side, then that. Hydrogen is in the back, so I'm looking at that correctly. And notice the movement, OH, change, and that. So I'm looking at that clockwise. It is R. Since this is the same, I'm going to say R. Now, at the other center, notice that we have like 3 carbon chains and the hydrogen in the back here, no drawn. And so what we need to define is which chain has higher priority. Here you have carbon attached to O and a carbon. Here you have carbon attached to another carbon, and then is the O. And here this carbon has attached to carbon, 2 H's. So highest priority is this one. This time I'm going to draw it because probably it's more difficult. And so next, we see this is hydrogen, carbon. And same thing here. So say carbon, hydrogen. And this one is attached to another carbon, hydrogen. But when you go to this layer, they are tied. So same thing, but if we go further, this is attached to oxygen, carbon, hydrogen. So this is higher priority because at the other carbon, this will be again carbon, hydrogen, hydrogen. So second highest priority is this chain, and there is that. So the other chiral center will be 1, 2, 3, so it's R again. So follow the numbers, 1, 2, 3. Hydrogen is in the back. Now, for the oxygen, the carbon that has the oxygen substituent, the hydroxyl substituent, we say oxygen, then this side, so we have this 2 sides, right, in the ring. This side has this substituent, so this higher priority. So we go 1, 2, and then 3. So it's also R. So notice this diastereomer is RRR. And now, what are the configurations at the diastereomer? Well, the center is the same, but now this is inverted, so it must be S, and the other must be S. So they are related as diastereomers. Let's do one more here. Let's see. This, I think, is easy, but we need to remember things. So now, these 2 molecules, let's see what is the relationship between these 2. Here we have 5, 6 carbon, 1, 2, 3, 4, 5, 6 carbon, C6. And then we have, if you count, You have 2, 4, 6, 8, 7, 8, 9, 10, right? So 10 hydrogens. If you do the same here, it is the same molecular formula, but the atoms are connected different, so they are constitutional. Constitutional isomers. So they're not stereoisomers. These two are stereoisomers. So the bottom one is constitutional. So now let me do something else. For that, I will need to erase one of my problems. And let's do one more. Just one more, and then we do more in another video. Okay, so let's see which one I pick here. Okay. These are metal groups, okay? When you don't put anything, it's because they're metal. And now I have these other drawing. Right, so they look a little bit different, right? But turns out they have the same number of carbon. Notice that here you have methyl, ethyl, same thing here. Then you have the other carbon has this carbon right here is another chiral center. And if you notice, here it has a metal in this chain, 1, 2, 3, 4, so a butyl. And here you have a metal and a butyl. So it's the same. And here you have another chiral center, so metal, ethyl, and all that change. So these are the two chiral centers. Maybe not evident at first, but here let's determine the absolute configuration. So doing that quick, let's say highest priority at the carbon here, and would be, let's just give it 1, 2, 3, carbon 3, down 4, and assigning the lowest number possible to where the substituents are, right? So that's why I'm choosing to write numbers from this side to the other side and not the opposite. So it will be 3, 4 dimethyl, octane. And actually, that's the same. If you do 1, 2, 3, 4, 5, 6, 7, 8. And these are the two metals. So the same name. Now we're doing just the absolute configuration for those. For carbon 3, because we need to add that portion to the name. So we need to say 3, whatever configuration we find, and then carbon 4. So let's see what happened. At carbon 3, highest priority is the chain to the right, and then second highest is the side. So I'm going to go 1, 2, 3. Notice that I'm doing this rotation, but I'm looking at that incorrectly because the lowest priority group is away from my view. Lowest priority group is a hydrogen that was not drawn. So even though I rotated this way clockwise, the configuration is S. So it's 3S. And then let's see what happened at carbon 4. So highest priority will be this side, because notice here's a ramification. So we have highest priority. Let's do another color. So highest priority this side, then this side. So we're going to go 1, 2, 3. But again, the hydrogen is, you're looking at that incorrectly because the hydrogen is pointing towards you. So whatever you find here following the numbers is the opposite. So we will do 1, 2, 3, looks like our, but the configuration is S. So this is the 3S, 4S, 3,4-dimethyl octane. And so this one, if you do the same strategy, actually notice that here the metal and the hydrogen are switched. So the configuration here should be R. And now when you look at the configuration of the other carbon, here you have a metal. You still have the hydrogen in front of you, but you have switched two groups. You have switched the metal, which is in a dash here, and with this. So switch those two groups, leaving the hydrogen the same way. So this will be inverted as well. So when the two centers are inverted, then we have two chiral centers. These two are related as enantiomers. So recap, do the absolute configuration. Well, we assigned it the name, and in the name you must include the absolute configuration. But the first step always is determining how many chiral centers do we have. And the total number of a stereoisomer is 2 to the n, where n is the number of chiral centers. But the point is here, after we do that, determine the number of chiral centers, notice what are the configurations. And if they're all inverted, then the relationship of the two molecules is they are enantiomers. We'll do more problems about this.